So, welcome everybody. Today we'll be looking at measurement as well as scalars and vectors. So, without wasting any more time, let's jump right into it. Now, I believe that all of us have an idea of what measurement is, right? Measurement is a process of knowing the quantity of a particular physical or the amount rather of a particular physical quantity. For example, it's not just enough to know that when you have maybe headache, for example, you have to take paracetamol or this drug. You need to know the measurement that is to be taken so that you don't have an overdose. So also in physics, like you need electricity, but you need to know what is the amount of electricity that you need in your house so that you don't take a maximum load or an overload of electricity or current that can lead to overheating or burning. So it is a process of comparing an unknown physical quantity with a known standard quantity of the same kind. That means you can compare an unknown physical quantity with a known standard quantity of the same kind. That's why we have what are called standards of measurement, right? Those are the standards of measurement. It is through the standards of measurement that you are able to take accurate measurement. Now let's look at the first one. Measurement of length. What is the unit for measuring length? We know that the standard unit for measuring length is in meters. And the instrument used for measuring your length are your meter rule, your tape rule. But in physics, most likely we use the meter rule. We also have your vernier calipers, which is used for accurate measurement of internal or external diameters with a least count or degree of accuracy of 0.01 centimeters. I'll still explain more as we go deep. Now, there are many instruments used for measuring your length. Number one is the meter rule, and the accuracy of a meter rule is 0.1 centimeters. That's why, for example, the meter rule uses in 0.1, like this is what I mean. When you draw your meter rule, you have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, then 1. So you see each of them is 0.1 centimeters. So that's the degree of accuracy of your meter rule. While your vernier calipers has a degree of accuracy of 0.01 centimeters and is used for measuring internal and external diameters. Okay. Now, like in the case of this vernier caliper here, if you look at this point right here, it is used to measure the internal diameter. You can see this object being placed in it, and then the vernier caliper is used to measure its internal diameters. While the other end of your vernier caliper here is used to measure external diameters. And as you can see here, this object is external diameter here is being measured. Now let's see how to take reading from the vernier caliper. How do you take reading from your vernier caliper? It is your main scale plus your vernier scale. Now look at this reading that we're giving here. And we are asked what reading is indicated. Let's check the main scale. So looking at the vernier caliper, we have 1, 2, 3. Yes, 3 centimeters. Then I have 1, 2, 3. That means I have 3, 0.1, 0.2, and 0.3. So on the main scale, they stopped at 3.3. So I note it down somewhere. The main scale is 3.3. And then from your vernier scale, let's draw it out. So here's my vernier scale. Here's my vernier scale. So for my vernier scale, you check where it coincides or meets with the main scale. Now look at this point. I have 1, 2, 3, 4, 5, 6, 7. So it meets it at 0.7. So that will be, remember, the degree of accuracy is 0.01 centimeters. So it's going to be 0.07. So adding it together, what's going to be the reading of this vernier scale? It's going to be main reading plus the vernier scale reading is going to be 3.37. And in this case, this is option B. Let me come again. In order to take reading for your vernier caliper, you take the main scale. In this point, I have 3.1, 0.2, 0.3. So the main scale is 3.3. For the vernier scale, I have 1, 2, right? Sorry, let me come that. I have 1, 2, 3. Then if you check the point where it coincides with the scale, here is 5, here is 6, and then here is 7. So it's at the 7th mark that it coincides. So that point is going to be 0.07 on the vernier scale. So adding it, I have 3.37. Now, another instrument used to measure your length is your micrometer screw gauge. As the word micrometer implies, it is used to measure small length, like the thickness of a wire or of a paper. You insert it here, just at the teeth of the micrometer screw gauge, like here, you have the object, and then you tighten it and take the reading. Now, how do you also measure from a micrometer screw gauge? Same way, you take from the main scale and add it to the vernier scale. Now, the degree of accuracy of your micrometer screw gauge, because it is used to measure very, very tiny length, is 0.01, but in this case, millimeters. So it takes what? Millimeters. Let's see if we can have an example. We'll take an example from the JAMB past questions. Now, what are the precautions you need to use when you are measuring with length? You need to avoid your zero error and ensure proper eye alignment. Now, that error is called parallax error. For example, if a beaker is filled with water, you don't put your eye at this point and look up here in order to take measurement. You have to ensure that you are looking straight at it so that you can see what level it coincides. So if you look at the reading from a wrong perspective, that error is called parallax error. Parallax error. So moving on to the next, which is area. Now, the unit of area is in meters squared or squared meters. And of course, we know basic shapes like your rectangle. Area of a rectangle is length times breadth. Area of your circle is pi r squared. Then moving on to volume. Volume is measured in cubic meters, right? Because volume is basically length times breadth times height, which is meters length, meters unit of breadth, and meters also the unit of height. So the unit of volume is going to be meter cube. Okay. Now, there are specific shape and their volumes. Of course, this is not mathematics, but I just decided to state it because I know some of us may be doing mathematics. So, volume of a cube, a cube is a 3D version of a square. So, this is a cube. So, volume of the cube is equal to s cube, where s is the length of one side. Volume of a cylinder, this is a cylinder, is equal to pi r squared h. Now, for irregular bodies, the volume is determined using the displacement method. That means with a measuring cylinder. What happens is this. You place the irregular object, maybe a stone, into a displacement can. And so you put a measuring cylinder below it. Now an object, though that's another topic. An object will displace its own volume inside a fluid. So you now measure the volume of water that is displaced into your measuring cylinder. Whatever volume of water that is displaced will be the volume of the the irregular object. For example, like a stone is an irregular object. There's no formula for looking for the volume of a stone. So you put it inside a displacement can and measure the volume of water it displaces. Whatever volume of water that it displaces, it is volume. The next parameter to measure is your mass. And what is mass, if I may ask? Mass is the quantity of matter in a particular body. Like as human beings, your mass is made up of your kidneys, your liver, your lungs, your internal organs, your external organs, because that's what makes up your composition as a human being. So the SI unit of mass is in kilogram, and mass is measured using a beam balance or a Buckert balance, but the most generally acceptable one is the beam balance and also the chemical balance. So like I said, mass is measured by comparing an unknown mass with a known standard mass. As is with all cases of measurement, you always have a standard unit of what? Of measurement. So the next one is time. Now, what is the unit of time? Time is a time frame for which an event takes place, right? So the SI unit of time is in seconds, and there are many instruments used for measuring time, like your clock, your stopwatch, your digital timer. In the olden days, your pendulum clock, even your sound clock. Those were old instruments used for measuring time. The next is your fundamental physical quantities. Fundamental physical quantities are also called independent quantities, and they are quantities that don't depend on other quantities for their meaning. They are independent. For example, like I said, your length is independent. Once I tell you that the length from this point to this point is 5 centimeters, it's independent. The meaning is very, very clear. You don't need another thing to understand length. You just know the length is the distance between 2 points. That's all. So length is measured in mass. Then you have, your length is measured in meters. I beg your pardon. I wanted to say the next one is mass. Mass is measured in what? Kilogram. So these are fundamental quantities. Your time is measured in seconds. Now, JAMB mostly focuses on these three, mostly MLT. Though we have many others. We have your electric current. Your electric current I is measured in amperes, capital A as a symbol. Then you have the temperature, which is the degree of hotness or coldness of a body in Kelvin, not degree Kelvin, in Kelvin, K. You have the amount of a substance, which we are very conversant with from chemistry, which is measured in mole, right? And then we have luminous intensity, how bright an object is, which is measured in candela, CD. So these are all, there are 7 in number. These are called fundamental or independent quantities. They don't depend on other quantities for their meaning. They are independent. Once I tell you that the time is 5 o'clock, you don't need another physical quantity, right? And most times they can be measured directly. They can be measured directly using the appropriate relevant apparatus. The next one are called your derived physical quantities. These are quantities that are made or that depend on the fundamental quantities for their meaning. Let's take, for example, area. Area is not a fundamental quantity because it depends on another quantity for its meaning to be derived. So for example, if I'm looking for area of a rectangle, I have to do length times breadth, of which these two things are both length, hope you know. Whether you're calling of this length or the width, they are both lengths. Only that they have length across different parts. So that means area in itself is not fundamental, but it depends on fundamental quantities. That's what the unit of length is in meters. Breadth, which is also a different kind of length, is in meters. And the unit of area is in square meters. Another example is your velocity. In itself, velocity is still been talking about the rate of change of displacement with time. That means how fast are you going, right? How fast are you going? So that means velocity in itself is not a fundamental quantity. Instead, it's depending on another or 2 other quantities. That means how much distance are you covering per unit time? Because it's not just about, like for example, if you are going home or if 2 people are going home, we'll get home at different times, even if the distance is the same. Why? Because of how much distance I'm covering per time. If I'm covering more distance in a short while, that means I have a greater velocity, right? Or speed in layman term. But if you're covering short distances or displacement in shorter time, that means you have a smaller velocity. So you see, velocity in itself is not independent. It depends on the distance you're covering or the displacement and the time taken. So we also have acceleration. Acceleration is change in velocity over time. or basically you can see acceleration is, are you speeding up, or in the case of deceleration, are you speeding down, as I may call it, or slowing down. So acceleration is what is also not fundamental. It is not independent. It is dependent on the speed and the time. So another example is force, which is mass times acceleration. That's why the bigger the mass, the larger the force, right? If I punch you, the force generated is, directly proportional to the mass times the acceleration. Acceleration means, like I said, the speed, right? So if like a bus moves fast and hits you, you experience a great force. So force in itself is about the mass and the acceleration. Like a bicycle too can hit you at the same speed, but it won't have the same force as a car. Why? Because the car has a greater mass, unlike the bicycle, which has a smaller mass. So even if they use the same acceleration, because the mass of the car is greater, it will produce a greater force. So force depends on the mass and the acceleration. Was it speeding up when it hit you, or was it not? Now we now have determination of units. The unit of a derived quantity is obtained from the unit of the fundamental quantities involved, just like I said. I give an example of area. Area is length times length. Doesn't matter the length, whether length times breadth or length times length, like in a square. It's going to be now having length is a meters times length, which is a meter. So the unit of area is a meter squared. If it is small length that is measured in centimeters and centimeters, the unit is going to be centimeter times centimeter, which is centimeter squared. So the unit of a derived quantity depends on the fundamental quantities involved. Like velocity is displacement over time. Displacement is distance traveled in a particular direction. So what's the unit of distance? It is in meters divided by what's the unit of time? It is in seconds. So what will be the unit of speed or velocity? It is going to be meters over second, which is meters per second. So dimensional analysis is now the process by which we show how a derived quantity depends on the fundamental quantity. Let's take an example. Velocity is displacement over time. Displacement over time. So what is displacement? Distance, right, which is a length, over time, which is t. So the dimensional analysis of velocity is going to be L over t, which is going to be t raised to the power of minus 1. So by doing this, I'll be able to show that velocity, which is a derived quantity, is dependent on length and time. And this is also used to verify formulas, so that's for a different scope. Mass is equal to mass times acceleration. Now what is mass? Mass is a fundamental quantity, right? So I leave it in its unit. Mass is still a fundamental quantity, so I leave it as mass. Acceleration is velocity over time. Velocity is still a derived quantity. Time is fundamental. So you see, the essence of dimensional analysis is to show how derived quantities relate to the appropriate fundamental quantity. Here is fundamental, but here is still derived. So all I do, I relate it back to its own fundamental quantity. Velocity is distance over time or displacement over time. That's only velocity. Don't forget, you're also dividing by t. So that means now, in this case, my velocity will be mass times. Now, many people will make a mistake here. Don't make that mistake. Don't forget, this L over t is only velocity, which means L over t is together. So I'll leave it as L over t, then divided by t. Don't go and say t divided by t, give you 1. No. L over t came together with your velocity, so I'll leave them together, then divided by t. So it now be mass times L over t. Your division will change to times. Here can be written as t over 1. 1 will come up, t will come down, which will be 1 over t. So what would this give me? To be m times L. L times 1 is L. Then divided by t times t is t squared. And from the law of indices, it will give me ml t raised to the power of what? Minus 2. When you have divided by power, that becomes negative. So the dimension of force is mLT raised to the power minus 2. And from here, you can get the unit for force. Mass is in kilogram, length is in meter, time is in seconds. So this is raised to the power minus 2. So that means the unit of mass is kilogram meter per second squared. Kilogram meter per, this is divided per second squared, which is also called 1 Newton. So let's look at another one. Let's say pressure. So I didn't give that example. Let's say pressure. Pressure is force per unit what? Area. Now we've gotten the dimension for force. Force is mLT raised to the power minus 2 divided by area. Now what is area? Length times length. So 1 can cancel 1 here. So pressure is now equal to mT raised to the power minus 2 divided by L. Remember, when you have divided by, whatever power is here will become minus. So m divided by L raised to the power of minus 1 will not be divided by L raised to the power of 1 will not be L raised to the power of minus 1 because of this division here. Make this power negative. Then T raised to the power of minus 2. So this is the unit of pressure. From here again, this is dimension of pressure. From here again, you can get the unit. Mass is in kilogram, length is in meter, so it will be meter raised to the power of minus 1. Time is in seconds. So you can say it is kilogram per meter per second squared, right? Which is one of the units of what? Of pressure. Now, what is the use of dimensions? It is used to determine the unit of physical quantities like we've been doing. When you get the dimension, you can get the appropriate units. It is also used to check the correctness of an equation. Let me give you an example. You have an equation of motion which is V equals to U plus AT. Now, if this formula is correct, each part must give me the same dimension. It's called homogeneity. Now, we've gotten the dimension of velocity as displacement over time, which is LT raised to the power of what? Minus 1. We've done that here, as you can see. So velocity gave us what? Where is velocity? Yes, velocity gave us LT raised to the power of minus 1. So let's plug it in here. So velocity is LT raised to the power of minus 1. U is also initial velocity, so it will basically have the same dimension, which is LT raised to the power of minus 1. You can see this part and this part have the same dimension. Let's see if AT has the same dimension. If it does not have, that means this formula is wrong. So acceleration is velocity over time, right? So acceleration times time. Let's do it somewhere. AT. Acceleration on its own is velocity over time, then times time. So T will cancel T. So the overall dimension will be that of V, which is still LT raised to the power of minus 1. So you see that for each part, they have the same dimension. So dimensional analysis has proved that this formula is correct. So that's one. Then lastly, it is also used to convert between different systems of units. Now remember, for force, I told you that one of the units of force is what? Kilogram meter per second squared, which is also called what? 1 Newton here. Kilogram meter per second squared, which is called Newton. Since the unit of force is Newton, that means 1 Newton is equal to 1 kilogram meter per second squared. Now, what causes limitations of your experimental measurement? Number one is the accuracy of the measuring instrument. Accuracy means how close is it to the measured value. And also there is error. There are errors rather. Number one is instrumental defects. If the instrument is faulty. Also poor observation. If, like I give you an example of parallax error, you have to ensure you are reading at the right level. You don't just have a reading and you are trying to get the reading from below. You are looking at it. Let's say this is your head position. You're trying to read it from here. No, it's not right. Your eye level must be directly looking at it so that you can see the correct measurement. Then there's also environmental conditions, like doing some certain conditions, doing some measuring instruments may be affected. Their sensitivity may be affected, which will lead to them giving you but inaccurate readings. So what are significant figures? Well, just to mention that significant figures show the degree of accuracy of an instrument. For example, let's say if I have 0.00043. Now, these zeros here are not significant. So my first significant figure here is 4 and 3. So this is to 2 significant figures. So your leading zeros are not what? Are not significant. Also, zeros between non-zero digits are significant. For example, if I have 0.101, because this is between two non-zero digits, just like 2 of us will protect you. Normally, the 0 is not supposed to be significant, but because it's between 1 and 1 here, the 0 becomes significant. Then we have standard form. Standard form is a way of writing numbers in the form of a times 10 raised to the power of n, where a is a number from 1 to 9, right? So instead of writing large numbers like 3900000, you can just write it in standard form. So if I move here 1, 2, 3, 4, 5, 6, I'll have 3.9 times 10 raised to the power of 6. Now, why is this one 6? Because the place value is increasing from units, tens, 100, 1,000, tens of thousand, 100 of thousand. It increased. But if it reduces, let's say for example you have something like let me take this example, something like 0.00029. In standard form, you must have a number between 1 and 9. So here is 0 point something. It's not acceptable, so I'll move it. Here is still 0 point something. Moving it. It's still 0 point something. Moving it. Then moving it here. That's why I now have 2.9 times 10 raised to the power of, how many times did I move? 1, 2, 3, 4. 4. But because the place value is reducing, because here is units, is the only whole number. Here is tenth, hundredth, thousandth, tenth of thousand. Because it reduced, it will be what? -4. So basically, that's how you measure what? Standard form. So it is used to make sure that we're not writing very, very large values. Then we now have scalars and vectors. What are scalar quantities? Scalar quantities are quantities that have magnitude. What is magnitude? Numerical value. For example, your mass. You can say my mass is 50 kg, like a bag of rice or a bag of cement. It is 50 kg, but there's no direction. I cannot say 50 kg to the north or 50 kg to the south. They have magnitude, but there's no direction. The time is 12 o'clock. That's all. There's nothing like 12 o'clock to the north or 12 o'clock to the south, right? Temperature is 50 degrees Celsius, or maybe the temperature is 10 Kelvin, or it is 10 degrees Fahrenheit. Are you getting me? There is no direction. Speed also. Speed is maybe 20 meters per second. There's no direction. Then we now have another classification of quantities which are called vector quantities. Vector quantities are quantities that now have direction. They have magnitude, which is a numerical value, a calculated value, and a direction. Let me give an example. Distance is an example of a scalar quantity. I can say the distance is 50 meters. 50 meters can be measured even anywhere. Are you getting me? From my house, I can measure 50 meters. From your house, you can measure 50 meters. But if I'm saying something like the distance between Abeokuta and Oyo or maybe Ibadan is 50 meters. Now, this one is distance in a specified direction. So if you just go 50 meters, maybe anyway, you can measure or you can walk a distance of 50 meters, then you have not done what I asked you to do. If I ask you to take 50 meters from Abeokuta to Ibadan, because I've specified the direction of the 50 meters. Like I said, just saying 50 meters, if I say walk 50 meters, it's a scalar quantity. There's no direction. You can walk 50 meters or jog 50 meters from your house. But if I say walk 50 meters from Abeokuta towards Ibadan, that is now displacement. There's a direction given. Are you getting me? Another example is velocity. In speed, you can just say I was speeding, or my vehicle was moving at a speed of 20 meters per second. But for velocity, you can hear something like I was speeding, or I was moving at a speed of 20 meters per second towards the police checkpoint. That means there's a direction now. I was coming towards the police checkpoint at 20 meters per second. Then force too, force. In basic science, we're taught that it is a push or a pull that changes the uniform motion. But of course, we now learn that there are other types of forces that does not involve contact. So that means force has direction. Maybe I punched you. There was a direction in which I punched you, or I pulled you. There was a direction to which I pulled you. So there's what? There's a force. Now, the next thing is relative velocity. Relative velocity is the velocity of one object as observed from another moving object. Let's look at this. If I am moving from left to right at a speed of 3 meters per second, and you too, you are moving from left to right at a speed of 3 meters per second. Now, relative to me, you are not moving because we are moving in the same direction and in the same speed. So to me, it's as though you are just stagnant and following me. So that means we are not what? Relative to me, you are not what? You are not moving. Do you get? You are not moving. So in relative velocity, we're measuring that velocity as observed from another moving object. Now let me give another example. Now if you are on a bus, there are many passengers in the bus. Now if somebody is outside, relative to that person, you are moving because he's looking at you in a bus that just sped past him. But between me and the other passenger, relative to each other, we are both not moving because both of us are seated in the same bus. So relative motion is just based on the observation. That means the point of view. So to the person outside, I am moving, but to the person inside the bus, you are not moving because you both are seated in the same bus. So I remember what I said. Scalar quantities are quantities that have direction. They have magnitude but no direction. Then vector quantities have magnitude, they have a value, and they also have direction. So we now have resolution of vectors. Since vectors have direction, we can resolve them into horizontal and vertical components. Let's say this is a vector making an angle of theta with the horizontal. We have two directions we can use to check it. We have the horizontal direction, right, which I will call fx, and we have the vertical direction, which I will call fy. So this is the vector. Let me call it a force. So to get the horizontal component, using SOHCAHTOA, and TOA, we have for horizontal now. So I'm looking for, here is vertical and horizontal. Vertical and horizontal lines make 90 degrees. So that means this is a right angle triangle. That's how I can use SOHCAHTOA. Now, in this case, I'm looking for the horizontal component, which in this case is the adjacent. Here is your hypotenuse side, which is facing the 90 degrees. Then here is the opposite side, which is facing the angle. It is the side opposite the angle. Then the last side, which is your fx, is your adjacent. So I have my adjacent side in relation to the hypotenuse. So what is that? Adjacent and hypotenuse is k, which is cos. So cos theta is equal to adjacent, which is f of x, over hypotenuse, which is what? F. So f of x, which is the horizontal component, if you cross multiply, will be equal to f cos theta. Now don't forget, this theta must be in the horizontal, is the angle with the horizontal. So for a vector, which makes an angle with the horizontal component is f cos theta. Now if I want to get the vertical component, which is fy is my opposite, right, in relation to the vector itself, which is my hypotenuse, which is sine. So sine theta is opposite, of which that opposite is my what? Fy. So I have sine theta is opposite, which is fy, then over hypotenuse, of which the hypotenuse still is your f, or the vector. Hypotenuse is still the vector. So it's going to be over f. So the vertical component fy, if you cross multiply, will be equal to f sine theta. So this is the value of the vertical component. Then we have the graphical method, which we will deal with under equilibrium of forces. We'll deal with those under equilibrium forces. So we also have resultant, which is one single force that we have the same effect as two or more vectors. For example, if I have a vector coming in this direction and that vector going in this direction, instead of having two forces, the goal is to move from here to here, right? I can just have one line that will do that, move from here to here. That single one vector that can do the work of more than one vectors, that has the same effect, is called the resultant. So let's now begin to take some past questions so that we can practice what we've learned. Okay. Now the first question here says, the internationally agreed system of units for physical measurement are dash. So which of these are the internationally agreed system of units? No, SI units are the units for your fundamental quantities. Their units are called SI units. So the answer to that is question 1. Question 1 is option C, which is kilogram. Kilogram is the unit for mass, meters, which is the unit for length, and second, which is the unit for time. So the answer is C. Question 2 says, to determine the weight of an object, you could use dash. So to determine the weight of an object, you could use a beam balance. Now, beam balance is actually used to measure mass, not weight. Mass and weight are not the same. Weight is a force with which the earth pulls you down to its center, while mass is the amount of matter or the components that make up what a piece of matter. So it can be a beam balance. B says use a spring balance. Now, a spring balance is used to measure weight, right? So spring balance is correct. Spring balance is correct. Let's check the other. Say find the force necessary to give it certain acceleration. That doesn't necessarily measure weight. Force is mass and acceleration. It doesn't necessarily translate to weight, except if the acceleration is acceleration due to gravity. So that was not specified. So that's not necessarily translating to weight. D says you use none of these methods. Not correct, because what you use to measure weight is already there, which is spring balance. Question 3 says, which of the following physical quantities is not a vector? Remember, vectors have magnitude but no direction. So what's the answer going to be to question 3? The answer is walk. Because what is walk? Walk is force times distance, right? Now, walk in itself is a scalar quantity. It is a measure of how much energy you've used. True or false? More energy used equals to more work done. So walk in itself is not a vector quantity. It is a scalar quantity because it is just a measure. There's no direction, right? So it is just a measure of the amount of energy you use. So the answer is walk. Question 4 says, an example of a scalar quantity is dash. An example of a scalar quantity is dash. Quite tricky. The options here are quite tricky. Velocity is a scalar quantity. Weight is a scalar quantity. Why? Because your weight has downward. It has a direction. If you sit down, if you carry somebody, you'll be feeling their weight pressing on you, right? So weight is actually a vector quantity. So the answer here is electric charge. Electric charge in itself has no direction. So it is not what? It is not a vector quantity. It is a scalar quantity. Question 5 says, which of the following readings represent the measurement of the length of a metal using a vernier caliper? Now remember, I told you vernier caliper have an accuracy of 0.01 centimeters. So that means whatever reading that is into 2 decimals in centimeters is most likely from a vernier caliper. And the correct option to that in question 5 is A, which is 5.16 centimeters. Question 6. Now, we'll not take it serially. I will just take all the necessary parts. Question 6 says, which of the following is not a vector quantity? Is force a vector quantity? Yes, it is. Now, altitude is not a vector quantity. Your altitude is your height. Your altitude is your height. It has no direction. For example, if I want to measure the height of this building, if I take it top to bottom or bottom to top, I'll get the same thing. So direction here does not matter. So your altitude, your height is a scalar quantity. All I just know that it is 5 meters. Doesn't matter whether it's from top to bottom or bottom to top. It will still be 5 meters. So direction is inconsequential. Now let's see. Question 8 says, for which of the underlisted quantities is the derived ml squared t raised to the power minus 2 correct? Now moment is force times distance. At least everyone should know the dimension for force, which is ml to the power minus 2. I've done that before. You could go back to the video. Times distance, which is in also a length. So it's going to be ml times l will give me l squared. Then t raised to the power of minus 2. So they said for which of these is the unit ml squared to the power of minus 2 correct? So for I, which is moment, it is correct. Work is also force times distance, right? Which is the same thing. Force times distance is correct. Then acceleration, definitely acceleration is not correct. Acceleration is velocity over time. Our velocity is L to the power of minus 1, which is displacement over time. Then over t again, which now give me L to the power of minus 1. Then I told you when you have divided, to change the power here to negative. So it will be L to the power of minus 1 minus 1. You're owing 1, you're owing 1. That's minus 2. So you see for velocity it does not have that. So the answer is I and II only, which is option D for question 8. Question 9 says, which of the following is not a fundamental SI unit? Which of them? The answer is radian. Radian. Because meter is a fundamental SI unit. It is for what? Length. Ampere for current. Kelvin for temperature. Second for time. Radian is not for a fundamental quantity. Question 10 says, which of the following statements are true about the spring balance and the chemical balance? Number 1, both are used to measure mass, the mass of an object. Is that correct? No. The spring balance is used to measure weight. Chemical balance is used to measure mass. So both are not used for mass. II says either of them may be used to measure the weight of an object. Still not correct. Chemical balance is for mass, while spring balance is for weight. So either one of them cannot be used to measure weight. Then let us proceed. The spring balance works on the principle of Hooke's law, while the chemical balance works on the principle of moment. That's correct. Because in the spring balance, this is the spring, there's a hook. When you hang the object, there's an extension that will not give you a reading on the scale. For the chemical balance, once you place it here, it works on the principle of moment. So that's correct. Option III is correct. Let's go on. IV says, a change in gravity changes the reading of a spring balance, but not that of a chemical balance. And that's correct, because a change in gravity changes the reading of a spring balance, because the spring balance measures weight, which is mass and acceleration due to gravity. So if gravity changes, weight changes, and the reading of your spring balance changes. But for your chemical balance, which only measures mass, it has no business with acceleration due to gravity. So the answer is III and IV, which is option C. Question 11 then says, which of the following represents the correct precision if the length of a piece of wire is measured with a meter rule? So which of them shows the correct precision? Now don't forget, your meter rule measures to 0.1 centimeters. Or if we don't forget, 10 millimeter make 1 centimeter. Now this time around, they wrote the units in millimeter to confuse us. But we'll show them that we know what we are doing, right? So let's see, if I divide here, both of them by 10, That means that what? Here I'll have 1 for millimeter. And for the centimeter, 1 over 10 will give me 0.1 centimeter. Now, since the degree of accuracy for your meter rule is 0.1 centimeter, it is also equivalent to 1 millimeter. So that means in the millimeter, it will be in whole number, of which the only one here in whole number is 35 millimeters. So the answer is A. So let's not bother ourselves and take these simple questions. Let's take difficult ones. Question 13 says, which of the following units is equivalent to kilogram meter per second? Kilogram meters per second. The first one says Newton per second. Second one says Newton meter second. Third one says Newton seconds. Now don't forget, force is mass times acceleration, right? Of which for force we got the dimension as ml to the power minus 2, which is mass is in kilogram, length is in meters, time is in per second. So this alone is called Newton. So 1 Newton is kilogram meter per second squared. But now they now said which of these is equivalent to kilogram meter per second, which means something removed 1 from this second. So if this is Newton, what will I do to reduce second from minus 2 to 1? I'll multiply it by 1s. This is what I mean. Since 1 Newton is kilogram meter per second squared, if you multiply it by s, what will you have? Kilogram meters. Now for the second, you have minus 2. According to the law of indices, times will change to plus, then 1 here. So you now have kilogram meter per second, because it's minus 2 plus 1. So that means which one will be equal to kilogram meter per second? It's going to be Newton second, which is option C. Question 14 is also simple. Should I skip? Yes, I think I should, but let me just do it anyways. So which of the following are the correct SI unit of the quantities indicated? We have Newton for force, I is correct. Then for torque, we have Newton per meter, that's not correct. Torque is turning effect of a force, which is force times perpendicular distance, which is Newton for force, then distance in meters, so it's supposed to be Newton meter, so that's not correct. Watt for power, that is correct. I is correct. Then for momentum, kilogram meter per second squared. Let's see. Momentum is mass times velocity, which is kilogram. Velocity is in meters per second, so it's supposed to be kilogram meter per second. All we have there is kilogram meter per second squared, so that's not correct. So the only answer is I and I, which is option D. We just take 16 says, which of the following is a set of vectors? Which of them is a set of vectors? Now, force is a vector, but mass is not a vector. That's out. Acceleration is a vector, velocity is a vector, and then moment is a vector. So without wasting time, 16 is B. 17 says, what is the reading of the vernier scale above? Let's look for the vernier scale. Good. So for question 17, let's take the reading of that vernier scale. Okay, very good. I'll have to draw it. Then here's my vernier scale. Now remember what I said. We must ensure to check where it touches the main scale. But if you look at it, it's at this point. At this point, if I count it as 1, or let me just write it out. 1, 2, 3, 4. So I think this is too much. I'll just clean this. Good. Now, if you notice something here, here is 2 centimeters. So if here is 2 centimeters, what is it going to be? Here is going to be 1.9, 1.8, 1.7. So here is 1.7, 1.8, 1.92 here. So here will be 1.8. So on the main scale, we have 1.8. Now on the vernier scale, we have to zoom in to see where it touches the main scale. Let me count. 1, 2, 3, 4, 5, 6, right? Here is 0 already. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's supposed to be 10 divisions. So we have to count to make sure we have 10 divisions. So I'll take here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No. So I'll take here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So here's 0, 1, 2, 3, 4, 5, 6, 7, 8. So it touches the vernier scale here at 8. Now don't forget your vernier scale is 0.01 centimeters, right? So that will be 0.08. So it's going to be adding it, main scale plus vernier scale will be 1 plus 88, 1.88 rather, which will give me what option? Option A, 1.88 centimeters. So let's see. Question 18 says, which of the following is a fundamental unit? I think you can do that. That is your second. So we're not going to solve all. We're just going to take different types. So question 19 says, what is the least possible error in using a rule graduated, or you can say marked, in centimeters? So what is the least error that is what? That is permissible. Okay. So now, least error is 1 over 2 times the place value. 1 over 2 times the place value. So here is 1 over 2 times, what is the place value? So the place value here is in centimeter, which is 1 centimeter, right? So 1 over 2 times the place value, which is unit, which is 1. So I'll have 1 times 1 is 1 over 2, which will give me 0.5 centimeters. So the answer to 19 is actually B. The answer to 19 is actually B. 20 says, which of the following quantities has the same unit as the watt? Watt is power, and power is what? Energy over time. So whichever one will give me the same thing as energy. Now energy is paramount to force, right? Energy is force times distance, or energy is paramount to work rather. The amount of energy you have determines the amount of work you do. So energy translates into work. And what is work? Force times distance, then all over time. So I can separate this as force times distance over time. So by doing this for question 20, all I have now, distance over time can be taken as speed, which is same thing with velocity, only that speed has no direction. So I can say force times velocity, which is option D. Which is option D. Alright. So like I said, we'll not be taking all the questions. We'll just take relevant ones. 22 says, what is the reading of the vernier caliper shown above? Now, before I do the answer, I want you guys to try it. So I'm giving you time. You can pause the video. So I think I can go on. So let's see the main scale. Main scale, I have 1, right? So where did it cut off the main scale? So where did it cut off the main scale? If you look at it, I have 1, 1.1, 1.2, 1.3 before the vernier scale came here. So main scale is 1.3. So we have no problem with that, 1.3 centimeters. Now for vernier scale, I need to find out where it touched the main scale. So here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so where did it touch the vernier scale? If you look, you see that it is along this line. Let me draw it. Along this line, you can see it where my pen is. So you have to count. So that's 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9. So remember 0 0.01. So that will be 0 0.09 in this case, which is, if you add the main scale plus the vernier scale, it is 1.39 centimeters, which is option C here. Now 23 says, which of these is the dimension for pressure? I've done that already. Pressure is force over area. Force is mLT squared minus 2 over area is L squared, which is L times L. So I have L cancel 1 L. So I have mass, then divided by, we change the power here to negative, which is L squared minus 1, then T squared minus 2. So what option is that? Option A. Question 24 says, at what respective values of x, y, and z would the unit of force, the Newton, would the unit of force, which is the Newton, be dimensionally equal to m raised to the power of x, l raised to the power of y, t raised to the power of z. Now we already know the dimension of force as m l t raised to the power of minus 2. So that means m is raised to the power 1. So if you compare it with this one, if this is dimension for force, so that means this dimension for force must be equal to this. So x will be 1, x will be 1, y will also be 1, and z will be minus 2. Z will be minus 2. So 1, 1, minus 2. So which option there is giving us the same answer? None of them. I believe maybe there's a typo somewhere. So the answer is 1, 1, minus 2. 1, 1, minus 2. 25 says the physical quantity that has the same dimension as impulse is momentum, basically. When we deal with the topic, you will understand it better. Impulse, remember, is equal to change in momentum. According to Newton's second law, impulse is force times time is equal to mass times velocity. Probably try it as an assignment. Check the dimension for both of them if they are the same. Force is ml to the power minus 2, then times t, then you know mass is m, and velocity is l to the power minus 2. I'm already even doing this here, so that I don't think there's any need, right? So you check impulse and momentum, do they have the same dimension? Then velocity is l to the power minus 1, Well, I think we can just quickly check that. ml to the power minus 1. So we check force is ml to the power minus 2, then times t. So now give me ml to the power of, when minus 2, this times we change to plus, then 1 here. Let's see if it's equal to ml to the power of minus 1, which will be ml to the power of minus 2 plus 1 will give me minus 1, which is the same dimension. So impulse and momentum have the same dimension. 27 says, which of the following consists entirely of vector quantities? It's very easy. Just look for anyone that contains scalar, disqualify it. For example, this one contains work. I told you work is a measure of the amount of energy you have. It's not a vector quantity, so that one is out. So for 27, that option is already, D is already out. So velocity. Now for option B, it has mass. So mass is a scalar quantity. It has no direction, so option B is out. I'm left with options A and option C. Now for option C, power is also time rate at which you are using your energy. That's why power is work over time or energy over time. So it's a scalar quantity. It's just a measure of how you are spending energy per time. So since this one has a scalar, it is out. So the only vector is velocity, magnetic flux, and reaction. 28 says the length of a piece of glass block was measured by means of a vernier caliper as shown above. The length of the glass block is dash. Now the drawing is not quite clear. Okay, I think it's we can manage it. It's not bad. So first of all, let's check the main scale. This is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. So the main scale is stopping at 1.6. Now the vernier scale, I need to check where does it coincide with the x-axis. Now that's the issue, where that's the place where I'm having issues. But let's see here, right? It is this line here under the 2. So I need to find out this is 0.1, 0.2, 0.3, and 0.4. So that's, remember, your vernier scale is to 2 decimal places in centimeters, so it will be 0.04. Once again, in case you are confused, let me zoom in. I told you to get the area of your vernier scale, check where that vernier scale meets with the main scale. Here is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to make sure that it is the same, right? So this is 0.1, 0.2, 0.3, 0.4 is where it meets back with the main scale. So it will give me 1.64, which is option B. But it's looking as though this point also joined, but since this is the first one that joined, that's what I'll pick. And besides, that looks more correct because here is 0.4, 5, 6, 7, 8, 9, and there's no one here that contains 9. That is if I'm checking the second one. So that's the answer, 1.64. So I think the rest are the ones that we can easily get ourselves. 29 again says the pair of physical quantities consists of vectors only. Now you can just disqualify A because speed is not a vector, right? So you can disqualify C, distance is not a vector. You can disqualify D, power is not a vector. So definitely the answer is B for 29. Now for 30, energy density. What is energy density? That's energy per unit volume, right? There's also energy per unit mass anyways, but energy density is energy which is paramount to force times distance, or work done, right, which is force times distance. So I can say work done per unit volume. Work done is force times distance all over volume, which is distance times distance times distance, or length times length times length. So distance can cancel distance. I will have force over distance squared. Force is ml to the power of minus 2 over distance, which is L squared. L will cancel 1 L. So I'll have m to the power of minus 2 over L raised to the power of 1. So if I'm writing it to give me m L raised to the power of minus 1 t raised to the power of minus 2. So which of them gives me that for energy density? Okay, they said the unit. So let's convert it. Mass is in kilogram. Per length will give me per meter. Then per time will give me per second squared, because this unit of time is seconds. So it's kilogram per meter per second squared, which is option B. Now for this one, if you don't know the formula, you'll not be able to apply it. So probably, like I've always said, always have a formula book. So energy density is what? Energy over volume. So I think with this, we are able to go on and solve all of them. Let me take 41. From the diagram above, the measuring accuracy of the micrometer screw gauge is dash. So let's try and wrap up that one. So let's first get the main scale. 0, 1, 2, 3, right? Let's see where the main scale is. just that this is not very clear. Now I'm looking at it, all of them are 4 point something, so let me believe that this is 0, 1, 2, 3, and then a 4 here, right? So main scale is 4. Now vernier scale, I have to check where does it meet with the what? With the main scale. Here is 15. Here it is 16, right? It's 16 that meets with this line from the main scale. 16, 17, 18, 19, 20, right? So which one meets with the line? It is 16. So vernier scale will be 0.16. Remember, for your micrometer screw gauge is 0.01 millimeters. So that's why it is 0 something. Unlike the other one that should be 0. maybe 1. That's for your vernier scale. So for this micrometer screw gauge is 0, 1, 2, 3, 4. Main scale is 4. Vernier scale, the one that coincides after 15 is 16. So adding it gives me 4.16 millimeters. So the option is D. 42 says an instrument whose accuracy is 0.05 easy dash 0.05 centimeters. Now this one is in centimeters. What is it going to be? What is it going to be? We'll have to check, right? Your meter is in 0.1 centimeters, so it can be it. Your vernier caliper is in 0.01 centimeters, 2 decimal places. So which is it going to be? It's going to be a vernier caliper, because this one is in 0.05 centimeter, 2 decimal places as well. So the answer to 42 is what? Is B. 45, we've answered it. 44 is also easy. Power is work done over time. From there, you can split work done into force times distance all over time. Then we know that force is ml to the power minus 2 times distance, which is L all over time, which will give me m. L times L gives me L squared. Then I'm left with T to the power minus 2 over T to the power 1. So this will be ml squared T to the power minus 2 divided, we change to minus, then you have 1. So it will be ml squared T to the power, you're owing 2, you're owing 1, you're owing 3. So the answer will be ml squared T to the power minus 3, which is option A. So basically this topic is very, very what? Simple. This topic is very, very simple. Once you understand the concept, you are very, very free to get all the questions that are available. Alright, so see you in class. At least this video is going to provide a form of support apart from the normal classes that we're going to have. So if there are any questions, do well to reach out to me. So in the meantime, thank you for your time and see you in the next video.